Hi everyone, this is Ehsan. Welcome to my channel and joining me. Today I'll introduce the finite difference method in computational mechanics following chapter 5 of computational fluid dynamics of Professor Anderson. But before we dive in, I have a warm-up question. Uh, what happens in a numerical method when you apply a scalar function like sine x to a matrix x? Please pause the video now, think it through and leave your answer in the comment. Great, let's get started. On this slide, you see the roadmap for today's talk. We began with motivation, the finite difference approach and its foundation in Taylor's theorem. Next, we'll derive our finite difference formula directly from the series and quantity the error introduced when truncating. After that, we'll review the common scheme, first order, forward, backward, and second order central and mixed derivative, and discuss how handle boundary with one side formula. Finally, we wrap up with key takeaway and point you toward further resources. At the heart of finite difference method lies Taylor's series or Taylor's theorem. We start by expanding our solution U in a Taylor series about a grid point, and then solve for derivative term. Concretely, to approximate ux standing for partial derivative of u with respect to x, we rewrite it as a combination of neighboring value ui plus 1j or ui minus 1j divided by delta x plus a non-truncated error. Applying this replacement for every derivative in governing PDE that I presented in previous clip, whether partial derivative with respect to x or partial with respect to y, convert the continuous equation into a set of algebraic equations defined at each mesh node. We then assemble these into a large sparse linear system, which we solve for the unknown nodal value like uij. Two factor control how accurate our approximation is. The one is grid resolution like delta x and delta y, and the order of difference including first order, second order, or higher order. Finer mesh and higher order formula reduce the truncation error at expense of a large standstill or more computational work, but they yield more precise solution. In practical simulation, whether in 1, 2, or 3-dimensional analysis, we must first discretize the problem domain. Figure 1 shows a typical 2D mesh. Each node on our Cartesian grid is uniquely identified by two integer indices, I in the x direction, j in the y direction. We call the current or pivot node P located at indices I or j. Its immediate neighbors are then I plus 1j to the right, I minus 1j to the left, I j plus 1 to the above, and I j minus 1 to below. At each of these nodes, we store our field variable. Field variable can be like temperature, pressure, displacement, or whatever quantity we're solving for as uij. From a programming standpoint, these indices must be mapped to memory or array position efficiently. A robust indexing algorithm not only speed up the access of IOJ, but also simplify the assembly of the discrete governing equation and the enforcement of boundary condition. As you expected, for 3D analysis, principles remain the same. Introduce third indices like name K. Use contiguous memory layout where possible, and keep your neighbor lookup. Uh, Using Taylor's theorem, we can express u at I plus 1 j in term of derivative at pivot point IOJ. This is EQ51. It is mathematically exact only if we keep infinitely many term and let delta x tend to 0, but of course neither is practical in computation. In practice, we truncated the series. If we neglect all term of order delta x3 and higher, we get a second order accurate formula. If we neglect delta x2 and above, we end up with first order accuracy. The higher order you keep, the better your local approximation, but also the more grid points you need in your stencil. These infinite sum are the truncation error you incur by cutting off the series. For example, for second order, we start at n equal 3. For first order truncated error, at n equal 2. To reduce error, you either add more term, raising the order, or refine the grid by decreasing delta x. Rearranging the Taylor expansion to isolate the first derivative, the leading term, and give the familiar forward difference, and the remainder is formally O delta x. We call this a first order forward difference scheme. Now, to derive the first order reward or backward difference, we express ui minus 1j in terms of the pivot value uioj. Using Taylor theorem, we expand ui minus 1j about the point ioj, which introduce alternative sign from the minus delta x n term. Equation 5 written equation 5 writes it into equivalent ways which we'll use to isolate derivative. Rearranging equation 5 to solve for the first derivative at ioj, the error term O delta x remind us this is only first order accurate. This is called the reward or backward difference formula. By subtracting the two Taylor series, the even order terms cancel, leaving only the odd power. Solving for derivative yield the central difference formula 5/8, which is second order accurate in delta x. To get the second derivative, we substitute the expression for the first derivative back into the Taylor series. The result in EQ11 is symmetric and also second order accurate. By exactly the same Taylor series manipulation in Y, we get forward, backward, central first differences, and the central second difference. The structure is identical to the x direction formula. Another way to see second order central second difference is as the forward difference of the reward first derivative. This perspective can help with generalizing to non-uniform grid or higher derivative. To approximate the mixed derivative, we take x difference of the y difference, plugging in the central standstill for each. We get the 4-point formula. It is also second order accurate in each direction. In summary, Taylor's series expansion gives us a systematic way to derive finite difference formula of any order. We've covered the common 1 and 2-point standstill, extended to second derivative and mixed formula. For a comprehensive table of even higher order and irregular grid formula, see page 44-45 of the reference text. Thank you for attention right here. If you have any question, leave the message for me. Now we reach the crucial question. At a boundary, we have no grid point below y equals 0, as depicted in Fig 5.2, so the usual central difference fails. In Fig 5.2, our standstill only extends into the domain point 1, 2, and 3. We want to formulate, for example, partial derivative of u with respect to y at point 1 using only u1, u2, and u3. Equation 15 is easy, just a forward difference from point 1 to point 2, but its error is the first order accurate of O delta y. Can we do better second order without needing u below the boundary? This is the challenge of applying the boundary condition. We fit a quadratic function as solution through point 1 to 3 at y equal 0 and delta y and 2 delta y. Substituting give three equations in for a, b, and c. Eliminating a and c yield b, which is the first derivative at y equals 0 with a second order accuracy. Equation 5.17. Differentiating EQ16 and setting y equals 0 tell us the partial derivative of u with respect to y at point 1. Substituting equation 17 give our final formula in 5.22 accurate to O delta y2. This is the standard 3.1 side difference at a boundary. Y is equation 20 second or is has the error of second order because our quadratic function assumption match the Taylor expansion up to y2, so the remainder is O delta y3 divided by delta y, drop the error to O delta y2 second order. In practice, for even higher order accuracy at boundary, you can use 4 or 5 point on one side standstill. To concluding, we've seen how Taylor expansion yields a systematic hierarchy of finite difference scheme: first order, forward, backwards, second order, central, and mixed, as well as one-side boundary formulas. Each choice balances standstill with accuracy and computational overhead. For me, for more advanced topic, higher order standstill, non-uniform mesh, and irregular domain, consult the recommendation chapter. in your reference text. Thank you for your attention. I'm happy to take any question. In continue, we dive in programming like MATLAB and Mathematica for solving the example problem. Have a nice time. Bye-bye.